Hello, everyone. Welcome back to the thrilling conclusion of Advent of Code 2020. It's day 25 today, so while this video is being released on the 26th, if you're watching this from the YouTube archives, I guess, Merry Christmas if you're into that kind of thing. We aren't actually going to be finished because I don't plan to go back and do part 2 of day 20. It just does not seem like a fun time. So for all you achievement hunters out there, you're going to be eternally frustrated by this, but I don't know. I'm not into achievements. I do the puzzles when they're fun. I didn't see myself having fun finishing that one. And it's not just because of time. You saw there was one I spent 3.5 hours on a couple days ago. Because I actually enjoyed doing that puzzle, even though it was hard. I was messing it up, but I was learning things, right? Anyway. So here we are, day 25, Combo Breaker. This is the first one that is not alliterative, by the way. It's a little interesting. It's the combo breaker, I guess. Very funny. You finally reach the check-in desk. Unfortunately, their registration systems are currently offline, and they cannot check you in. Noticing the look on your face, they quickly add that tech support is already on the way. They even created all the room keys this morning. You can take yours now and give them your room deposit once the registration system comes back online. The room key is a small RFID card. Your room's on the 25th floor. 25. And the elevators are also temporarily out of service, so it takes what little energy you have left to even climb the stairs and navigate the halls. You finally reach the door to your room, swipe your card, and the light turns red. Examining the card more closely, you discover a phone number for tech support. Hello, how can we help you today? You explain the situation. Well, it sounds like the card isn't sending the right command to unlock the door. If you go back to the check-in desk, surely someone there can reset it for you. Still catching your breath, you describe the status of the elevator and the exact number of stairs you just had to climb. I see. Well, your only other option would be to reverse engineer the cryptographic handshake the card does with the door and then inject your own commands into the data stream, but that's definitely impossible. You thank them for their time. Unfortunately for the door, you know a thing or two about cryptographic handshakes. The handshake used by the card in the door involves an operation that transforms a subject number. To transform a subject number, start with the value 1. Then, a number of times called the loop size, perform the following steps. Set the value to itself multiplied by the subject number. Set the value to the remainder after dividing the value by 2020, 1227. By the way, why not 1225? Kind of a mystery. Something special going to happen 2 days from now? I guess we'll see. The card always uses a specific secret loop size when it transforms a subject number. The door always uses a different secret loop size. The cryptographic handshake looks like this. Transforms the subject number as 7 according to the card's loop size. And then it does a bunch of other stuff that doesn't really matter. Well, I don't know, maybe it matters. Yielding transform the subject number of 7 according to the loop size, and that's the public key. And each of these two participants does that with their own secret loop size. Then they each transmit the public keys, which we have eavesdropped on, and we have. The card transforms the subject number of the door's public key according to the card's loop size. And the result is the encryption key. And the same thing happens if we transform the subject number of the card's public key according to the door's loop size. So this actually is pretty reminiscent of how it's a really basic kind of key exchange. The only reason it's feasible to crack is because the modulo is small. Right, it's only 8 digits instead of, a 256-bit int or whatever. And so we can just brute force it. If you can use the 2 public keys to determine each device's loop size, you'll have enough information to calculate the secret encryption key. For example, suppose you know the card's public key is this. You try it out and find out the loop size must be 8. You can use either device's loop size with the other device's public key to calculate the encryption key. and the encryption key is the output we're supposed to produce. So I don't totally understand yet why we would want to crack both of them. It seems like we only need to crack one. But obviously we're going to write a program that can like crack any public key, and so we might as well maybe crack both of them. I don't know. Anyway, let's get started. So our input is just 2 ints. And that seems like a good input then. Tuple map read lines where tuple of xy is xy. We certainly will not need applicative do today, and probably not lambda case either. I was kind of sad when I read this to see that we're having to run the process backward and like actually do the brute forcing, because the like when you do exponentiation modulo something, it like the modulus what am I trying to say? Exponentiation modulo some integer is, I don't know if it's quite right to call it a monoidal operation, or if it's like a field or a ring or a group or some nonsense. But it has a nice property that like there's a like typical algorithm called exponentiation by repeated squaring, right? Where suppose that you need to compute like 15 to the power of 9 million mod 71 or something, right? Maybe not 15, we'll say 13, so it's prime. You could like start with 13, multiply it by 13, by 13, by 13, and so on, taking it mod 71 each time, and do this 9 million times. But if you choose a large enough exponent, 9 trillion, that gets pretty expensive, right? Maybe you could do it, but it's like, it's expensive. So what you actually, typically you would do is this thing called exponentiation by repeated squaring. You can say, well, okay, this is actually, 13 squared. No. 13 to the, here, we'll make this an 8, simplify. 13 to the power of 4 trillion squared. And then you can do the same thing and say, oh, okay, this is actually 13 to the 2 trillion squared, right? And you have a smaller number of operations to do. And eventually you start getting to odd numbers, and you have to split them so that it's like, if eventually you get to like 13 to the third, which is like 13 to the 1 times 13 squared. That's not times. So you can do this, and it's like not that hard to implement. But the cool thing is that in Haskell, it's, well, okay, it's already implemented for you by the exponentiation operator, but not with the modulo stuff, right? If you want to insert a modulo operation after each of these things, you have to do a little more work. And it turns out that this kind of divide and conquer strategy can be implemented generically for any monoid, indeed any semigroup, if you have a default for when there's 0. And it understands how to, it's implemented generically, right, over any monoid. And so you don't have to write it for yourself when you want to do it like mod sum operator. It's just like it's there for free as part of the standard library, as long as you understand that the operation you're doing is monoidal and structure it in that way. So I was kind of looking forward to getting to do that, but we're not going to really need to do that. I don't know. We might like end up doing it for the final, like for part 2 or something, but we don't need it for part 1, I don't think, right? Well, do we? Once we've computed the loop size, we're going to want to, I guess, we might as well. Once we have the loop size, we have to transform the other thing's public key by the loop size. And in that case, I guess we might as well use that built-in facility for making that efficient. So I guess let's just do a few obvious things. We need to define modulo is an int. Modulo is 2020 1227. That's the modulo they all use. Initial subject are both ints. And initial subject is 7. Okay. So, what exactly is it that we want? We want a function find loop size that takes it just takes a public key, right? It's just int to int? Yeah. So the find loop size of n which is our public key. Well, let's give it a better name, public key. Is the number of times that you have to perform some operation to reach this public key starting from 7, right? Iterate, transform, on the initial subject, where transform of n is n times something's not right. The subject number stays the same. A number of times called the loop size, perform the following steps. So in our cases, the subject number is always 7, right? I never need it to be anything else. And our initial subject, actually, that's incorrect. We start with 1. Start with the value 1. That's why this was bugging me. N times initial subject. Oh, well, we can just simplify that. Ah, no, because I forgot that I have to mod it. Okay. Mod modulo. So if we were to say find loop size, one of the examples that they give me, here's a public key 8. Yes. And this other one I assume will give me 11. Yes. Okay. So that's easy enough. We've already handled prepare. So part 1 of door card, we have to find the public, or the encryption key. Let door loop equal find loop size door. Now we have that. And what am I supposed to do next? Transform the subject number. Okay. With a loop size, yeah, okay, so it might look kind of like like, why is this find loop size specialized to the initial subject? Why can't I reuse this same code for like transforming? And I guess I could, but the point is this one actually needs to inspect every intermediate value. Whereas once I have the loop size, I just need to run the loop that many times. You know what? Let's just see, like, what's the loop size of our door? Stack run. Stack or new, maybe not. Stack run. I assume it's large. It's not 8. Yeah, so we can run an operation 2.5 million times. It shouldn't be that bad. But we can actually run it like a very, very small number of times if we use the monoidal machinery I was talking about. So what I want to say is I want to define a new type. Exponentiation is an exponentiation of int. And I want instance. I don't really need a monoid, probably. Anyway, instance semigroup exponentiation where exponentiation A plus exponentiation B is A exponentiation of A times B mod modulo. Right? So I need to multiply by the subject loop size times. And it doesn't, strictly speaking, have to be in order because it's associative, right? That's the key to all of this. You can split it up however you like and reuse intermediate results, and that's what we'll get out of S times. Haskell S times. Takes a number of times and an operation and gives you a result. An operation, sorry, yeah, a number of times and an operation, like a monoidal here. A number of times a monoidal value and gives you back the monoidal value, or in this case, the semigroupal value. Okay, so we can then say let door loop size equal this in exponentiation x equal s times, which I need to import, and the number of times is the door loop size of exponentiation card, right? The card's public key in X. I think that's it. Yeah. It's a moderately large number. But something cool that I want to show you is like how fast this actually is. If we were to say like, I don't know, like let's say we did it by like kind of the naive way. Iterate times 45. We'll pick a prime number, 37. Iterate tick of 1, where tick n equals n times 31 mod 13 or something, right? And give me the like 500th element of that. Oh, really? You can't use wheres here? Okay. Fine, I'll inline it. One? Really? That's just a coincidence, right? Oh, I said... So, okay, there you go. We picked like 50, said do this 55 million times, and it's like, it's not fast. Kind of thought it would be faster than this, though. Stack Overflow. Yeah? Really? Why? Because nobody's ever looking at the result? But I feel like mod is looking at the result, isn't it? Huh. Well, that's a little surprising to me. If I decide to do it like 5 million times, it's actually probably still going to Stack Overflow, right? This is some laziness issue. 8. Okay. So it came back like not fast, but okay. Oh, actually, I guess I should use the actual the exponentiation things that I'm using. So let's say mod this. And it comes back in like not a super huge amount of time, but not quickly. Okay. But if I said s times this number, exponentiation of 1. Wait a minute. 31, I guess, is where I'm starting from. Right, doing it 0 times would yield 1. Okay. S times and exponentiation are both not in scope? Something wrong? Exponentiation, okay, I hadn't loaded the file. So let's let result equal in result exponentiation. It comes back like instantly with, by the way, the same answer, 14.9 million, right? Yeah. And you can put in absurdly large numbers here because it'll take an integer, right? So you can say, just do this like, I don't know, a quadrillion times or something. It's like, here's the answer, got it. Like, so anyway, it's just cool that you get that for free. And by the way, now we've tested it, it works. So I think we can just like run the program. Had I already run the program? I guess I had. I forgot. I thought that I was just showing the loop size before. Okay. Well, let's punch that number in. That's the right answer. Part 2. Yeah, I thought so. So every year, the part 2 that they give you on the last day is just finish all the previous puzzles. So the last day is only a single part, basically. And I don't want to go back and do the last one. So we're just going to read this and that'll be the end of things. The light turns green and the door unlocks. As you collapse onto the bed in your room, your pager goes off. It's an emergency, the elf calling you explains. The soft serve machine in the cafeteria on Subbasement 7 just failed and you're the only one that knows how to fix it. We've already dispatched a reindeer to your location to pick you up. You hear the sound of hose landing on your balcony. The reindeer carefully explores the contents of your room while you figure out how you're going to pay the 50 stars you owe the resort before you leave. Noticing that you look concerned, the reindeer wanders over to you. You see that it's carrying a small pouch. Sorry for the trouble, a note in the pouch reads. Sitting at the bottom of the pouch is a gold coin with a little picture of a starfish on it. Looks like you only needed 49 stars after all. You don't have enough stars to pay the deposit, though. You need 1 more. So, I mean, we can look at our calendar, and it looks almost finished. We got 2 days that aren't finished, right? The day that says finish all the other days, and the 1 day we actually didn't finish. And like I said, I think we're pretty much done here. I hope you guys enjoyed this, and if you have been following along at home, writing your own programs, I hope that has gone well for you. Or if you're not done yet, I hope it continues to go well. Thanks for watching, everyone. The Advent of Code series, I don't know, it's a popular one on the channel. You know, insofar as anything I do is at all popular, which is like not very. But it gets more views than most of my stuff, and I'm glad to provide sort of more niche content compared to like the YouTube clickbait stuff that is all over the place. And it's just nice to get people saying, wow, I was really excited about this. Here's some interesting stuff about the problem. Anyway, I'm just like going on. I don't really have anything in particular to say. I just can't like bring myself to wrap up the video. So thanks for watching, and I'll see you next time.